Okay, so if on example 4, if you want to go like back through and answer the other questions, that's fine. But the sketching is kind of the new part. So I went ahead and put this graph here, f prime, and we want to sketch the derivative. So the first important step is to pick a flavor. Let's see. I want to graph it in, how about burnt orange? There we go. Well, that's regular orange. Burn it. There we go. All right. So now if I'm sketching the derivative at these corresponding x values, I want to plot a y value that represents the slope of the graph at that point. So first thing we do, if possible, go to a place where we have horizontal tangent lines. And I see only one of them, right? At 3, there's a horizontal tangent line. So I know that that's going to be an x-intercept. Now, if you remember again, it said that the graph of f is continuous. So if f is continuous, that means it's defined everywhere. And the derivative here is not defined at 6, okay? So if the derivative is not defined at 6, the second derivative won't be defined at 6 either, okay? But we'll deal with that here in just a second. So what else can we do? Well, now we start analyzing. Remember, once you get the zeros, you figure out, first of all, what is the sign of the slope that I'm about to sketch? Is it positive or negative? And then how is it positive or negative? How is it changing? And again, you just relate it to slopes that are nearby. So it looks like maybe, like if I were to extend the graph to the left of the y-intercept, it looks like maybe there would be another horizontal tangent line at x equals 0. So because the derivative doesn't exist at an endpoint, I may put an open circle there, to start with, possibly. Now, what is it doing from 0 to 3? F prime is decreasing, so its slopes are negative. So again, I know that my derivative, which ends up being called the second derivative here, that's just the name of it, it's going to be below the x-axis. Now, how is it going to be below the x-axis? Well, this is where you just kind of draw a couple, right? We have kind of like a small slope there, and then right around here at the inflection value, that's where it's going to be the most negative. And then somewhere over here, it's kind of shallow again. So if you need to assign values, that would be like -0.5, maybe like -2, and then -0.5 again. So what are those y values going to look like? Well, it's going to be like maybe something here, and then maybe this at this x value, that's where it's the most negative, and then it starts coming back up. So something like this, right? And then you can come back and get rid of your little supporting slopes and values, all right? What's important though is that what appears to be the inflection value on the graph of f prime ends up being the local minimum, okay? And then what are we doing on the next interval? F prime is increasing, so the derivative is going to be positive. And where is the inflection value? Somewhere in there. So that's where it's going to be the biggest positive number. So I don't know what that's going to look like, but I'll increase up to a high point. And then again, if you were to actually like fill in that dot and continue, it looks like there might be a horizontal tangent line there. So that's kind of helpful if you want, because you could put wherever that is, you can put like an open circle again at 6, 0. But if not, just draw like a little tangent line. It looks like it could be +0.5. So I know that the slopes are decreasing. So even though the y values are still increasing, the slopes of this graph are decreasing. So it's going to come back down maybe towards the 0.60. It may even stop short of 60 because it may not go perfectly horizontal there. All right. And then to the right of 6, it looks like the function is increasing again, right? So again, I'm going to have positive slopes. And what are the slopes doing? Well, it looks like it's going to be like small positive to, and this is curved up the whole way to a greater slope. So after that, my slopes are positive and getting bigger. So it looks like it may be something like this. And then at 9, an open circle. Something like that. So now we just label it as f double prime. And again, that's kind of what's important. Again, is the inflection values kind of line up with the local max or mins. And there might be variations right around 6, but if f prime doesn't exist there, neither will the second derivative. Okay, so yours should look similar. All right, and then going backwards. So again, for going backwards, we're going to need a starting point. So let's assume that in this case, I give it to you as 0, 0, but let's change it up a little bit, because I told you sometimes they don't give you the starting value. Let's just say that, let's say that I'm given the point 3, 0. Now I'm trying to go backwards. You know, in other words, f of 3 equals 0. So I'm going to come over here and put that as my x-intercept. So now that's my starting point. So let's go ahead and graph it from that point forward, and then we'll just come back and finish it from 0 to 3. All right, so this is, I think actually this is probably the easier one, really, because all you got to do is look at it on each interval where either the y values change signs or the slopes change signs. So on this little interval here, we have negative y values, positive slopes. Negative y values, positive slopes. That's negative, positive. That translates to decreasing concave what? Up. Decreasing concave up, like that. Boom. And now because at 4 we have a 0, that's where f prime is 0. I need to go with a horizontal tangent line there. From 4 to 6, I have positive y values, positive slopes. Positive, positive means increasing concave up. Increasing concave up until I get to 6. And then I put an open circle. Or not. Well, maybe. If the function is defined everywhere, or it said it's continuous, then I can't really put an open circle. Okay, and it did say the function f was continuous. So let me just stop there. On the other side now, I have from 6 to 8, I have negative y values, positive slopes. Negative y values, positive slopes. So now that's decreasing concave up. Now, if the function is continuous, then from that point, I got to go decreasing concave up. And that's how you get your cusp out of it, right? And then I go horizontal at 8, because that's where the derivative is 0. And then from 8 to 9, positive y values, positive slopes. Positive, positive is increasing concave up. So increasing concave up to about right there. And we're not sketching the derivative, so I can put an open circle or solid dot. Yes.
So from 4 to 6.
Yep.
It's not concave down on f prime, so why would it go concave up?
Well, from 4 to 6, we have positive y values. And what are the slopes? We have positive slopes. We don't look at the curvature of f prime. We look at the y values and we look at the slopes. If the y values are positive from 4 to 6, then I know my function's increasing, right? If the slopes of f prime are positive, and they are, right? Positive slopes of f prime means f double prime is greater than 0. So f is cc up. You're looking at the wrong thing there. You're looking at the curvature of f prime. If you look at the curvature of f prime, you're looking at its second derivative. That's f triple prime information. No, we look at the y values of f prime, and that tells us if we're going up or down. And then we look at the slopes of f prime, which tells us if f is curving upwards or downwards. Okay, does that make sense? So it should then be, I think what I have it, increasing concave up. Okay. I'm just saying that given f of 3 equals 0. Yeah. So in the original notes, I said assuming f of 0 equals 0. But since we did that one yesterday, you're not always, that's might have been what they did like in 2010 and before. But every year they up their standards. So one of the things they might change it to this year, or I might change it to, is let's not give them the leftmost point. It's easy when you sketch from left to right. Let's give them a starting point that's in the middle of the graph, right? So now we'll sketch it from left to right. Now we'll back up. And let's go from 0 to 3. Now again, given f of 3 equals 0 for a continuous f, I got to make sure now that when I sketch from 0 to 3 that it ends up connecting with the point 3, 0. Okay.
I would say that it would never connect because it would never get low enough to ever cross.
Well, no, that's we have to be told something about f. And if we're told that f is continuous, we have to make it connect. Okay.
I did it off of f of 0 with this.
Right. You start with f of 0?
That's what the problem says.
Yeah, I know. I changed it. Yeah. All right. So now let's do it. It would still have to connect whether we started at 0, 0 or wherever. So I'm going to do this with a different flavor. Now, you do need a starting point, right? So let's just go ahead and start at I'll start right here. And then the nice thing about notability is I can make them connect afterwards by sliding it up or down. So that's where I'm going to start. Now, on this interval here, I have positive y values, negative slopes. Yes? Positive y values means f is increasing. Negative slopes of f prime means f is concave down. So I got to draw increasing, concave down. Increasing, concave down looks something like this. I'll just keep doing it until I get to 2, and then I go horizontally. Okay, because I do hit 0. And then from 2 to 3, I have negative y values, negative slope. So that's decreasing concave down. So decreasing concave down is going to look like something like that. Boom. All right. Now all I got to do to make them match up, because it said it was continuous, is just grab this. Whoa, not all of that. Sorry. It's just grab this. Oops. Sorry. Nope. Timeout. This, and then move it down. There we go. And now it's connected. So you might not always be given the starting value on the far left, but you will have to be given a point, okay? Because when you take the derivative to get f prime, the constant goes to 0. All right, and the only difference then among all the different solutions is a constant, right? +2, plus 0, -3, whatever. So all of these could be graphs of what we're going to call the antiderivative of f, but the one that's right here then is the only one that passes through the point 3, 0. Okay. So anyway, that's kind of slight modification on that question. Over your head? Does that not make sense?
No. It's,
Oh, okay. Okay. All right. I don't know if you're doing that. All right. So practice. There are questions on the worksheet. I did add questions to it. Let's take a look at that real quickly here. I don't want y'all to rush through it. I want y'all to make sure that you thoroughly understand it, because this is a summary of everything. And yeah, it is 14 pages. So let's see. Use all your math skills to graph them. There's only 2 of those. There's only 2 of them. Here's the table of values where you're answering questions. It's similar to what we did, except instead of a graph, then you're sketching it below. An actual free response question there from 97. An actual free response question there from 81. Back in the day, there was a lot more pre-calculus type questions on these. An actual AP question from 80, from 78. More, and then multiple choice. So the multiple choice should go a little bit more quickly. All right. So yeah, there you go. So anyway, we're going to finish the notes today. Today's Wednesday. We'll make this due Monday. Okay. Whatever day that is. So take your time with it. Make sure you understand it. And that's all I can say, right? Yeah. 14 pages. And again, hopefully you've already started it, right? By no means do I assign these like, 10 seconds before they're due. As soon as we start working on a section, or even before then, you can start working on the worksheet. I just don't assign like 20 problems a night, and go over them the next day. You have to manage your own time a little bit. Okay. So let's go ahead and finish then the notes. There's this type of question, okay, that makes a really nice multiple choice question. In fact, this example is a multiple choice question. Okay, so it says the function f is continuous on the closed interval from 5 to 7. Looks good. And it's twice differentiable on the open interval from 5 to 7 open. All that just means is we're going to be able to find the second derivative. That means that f prime is continuous, blah, blah, blah. If f prime of 6 is -3, and the second derivative is greater than 0 everywhere on the open interval, which of the following could be the table of values for f? Okay. The first thing you want to notice is, process, first of all, what it is that we're given. These are tables of values for x and f. They're telling us that f prime of 6 is negative. So that means at 6, f is decreasing, right? F is decreasing at 6. And then if the second derivative is greater than 0 on the open interval, then that means that f is what? CC up, right? CC up. But what else does it tell us? The second derivative, remember, always tells us two pieces of information. It always tells us the curvature of f, but it also tells us what f prime is doing. What is f prime doing? Increasing, right? So the slopes are increasing. All right. So it would appear then that at x equals 6, the function is decreasing at an increasing rate. Okay, so now here's how we use the table. If you notice, your x's, they should always kind of be the same increment, right? 5, 6, 7, 5, 6, 7, 5, 6, 7. But you got to be careful. Sometimes it could be like 5 to 6, and then it could be like 6 to 8, where it changes by 1, and then it changes by 2. But if they change by the same amount, +1 in this case, and then +1 again, or if it's +2, +2, or they're both +3, +3, that's what you want. You want your x's to change at regular intervals, whether it's 1 or 2, whatever, because then you can focus exclusively on the y values. All right. So here we go. If we know that f prime of 6 is negative, I know then that at least at that point, my function is decreasing. So let's look to see which of these have values that are decreasing. 10, 12, 16. Those aren't decreasing. It says, now, which of the following could it be, right? Not must be. That's kind of important. So even though I don't know what's happening, immediately to the right of 6, it would appear that these values are increasing. Okay, so just because the function is decreasing at a point doesn't mean it's decreasing on the interval. But I'm going to hold off on that. Okay, 15, 12, 9, those are decreasing, right? 17, 12, 10, those are decreasing. 8, 12, 18, those are doing what again? These are increasing. So not that that excludes it, but maybe not. I'm going to look at 14, 12, 8. Those are now decreasing. So I'm going to focus on the 3 that at least appear to be decreasing on the interval, even though it's only decreasing at a point. Now, if it is decreasing on the interval, it would have to be decreasing at an increasing rate. So now we look to see how it's decreasing, kind of like what we did with the graph where we looked to see if it was positive or negative, and then what they were doing compared to others. This one is losing 3, and then it's losing 3 again, right? So this one we would say on average is decreasing at a constant rate on average. Okay, not decreasing at an increasing rate. This one here from 17 to 12, we lost 5. And then from 12 to 10, we lost 2. That one is decreasing, but at a what rate? Increasing rate? Decreasing rate. Okay. And we want it to be decreasing at an increasing rate. Let's look at this one. 4 to 12, that's -2. And then 12 to 8, we've lost 4. So now we're starting to lose more rapidly, right? So that one would be decreasing at a increasing rate. Yeah. And then that would be the answer. Okay. So the other way to do it, if you're not sure from the data, is if you say decreasing at an increasing rate or positive second derivative, that would be decreasing in concave what? Up, right? Decreasing concave up would have to look something like that. You could actually plot the points, like if you're not sure, and it's all just kind of relative. So here's 5, 6, and 7. You would have to have like 8. Here's where you have to scale it the same way. 8, 9, 10, 11, 12, 13, 14. So here would be 12, here would be 14. So you'd say it's 5, 14, and then 6, 12, and then 7, 8. I'm sorry, decreasing. What did I write? Decreasing at an increasing rate. Decreasing concave up. What is this one doing? That's concave down, right? When we say it's decreasing at an increasing rate. Whoa, well, let's look at this one over here. Where was the other one? -5, -2. Let's plot those. I'll use a different flavor. -5 is 17, 14. So we got to count by the same. 8, 10, 12, 14, 16, 18. Here's 17. So that would be that one. And then 12 would be this one. And then 10 would be this one. That one's doing this. Ah. Is that concave up like we want? Oh, so guess what the answer is? C. All right. So why is that? Well, when things are negative, you got to be careful, right? Mrs. Skurhawk is still asking questions about this. If we have something that looks like that, we look at steepness versus slope, right? The tangent lines are getting less steep from left to right, yes? But what are the slopes doing? Increasing or decreasing? They're increasing, right? Because this slope right here might be like -8. This slope here might be -1. This slope right here might be 0. If a value goes from -8 to -1 to 0, they're increasing, right? So even though the slopes are, or the steepness is decreasing, they're getting less steep, the slopes, which are vectors, are actually increasing. So this is misleading, right? The difference is getting greater, but because they're negative, it's not what you think. Okay. So you got to be careful when you have negative slopes and they're changing. You got to be careful when you talk about how they're changing. Okay, because it can be counterintuitive. So when in doubt, graph it. All right. So that's why I put that one on there. I asked y'all they're decreasing at a what rate, and then I asked again, and y'all said it emphatically louder. But you can't. What is that? You can argue your point better by raising your voice, right? Right. That doesn't strengthen your argument. So just be careful. Just be careful. But that's how you do it. If you have positive slopes, then it's real intuitive, right? But be careful when you have negative slopes and they're changing. All right. So look at the differences and then look to see how the differences are changing. So that's how you do those data points. And there's one like that in the worksheet. So and I don't think it's the tricky one like this. Okay. All right. The last one, example 6, calculator. So I created this question just because I wanted to tie it back into statistics, and I want to tie it into I don't know, the calculator, but the inflection value as well. So the standard normal curve, which is known as the bell curve as well. You can read all that, but if you've had Kilford, at least you know then that social scientists use statistics a lot. You have one standard deviation from the mean. This is mu. It's kind of like the population average, which is really impossible to find. So there's ways to approximate that as well. And then you have one standard deviation away, which we call sigma. So this would be -1 sigma away, and then whatever that distance is, -2 sigmas. This would be +1 sigma away, 2 sigmas. And when you get out beyond 2 sigmas, approaching 3, you get pretty much the majority of the population. The area under this curve is equal to 1. Okay. Now it's kind of interesting. This kind of leads into improper integrals. I didn't draw it very well on that end, but there is a horizontal asymptote, and the graph will never touch the horizontal asymptote. So this is an unbounded region. If you look from left to right, it's unbounded. So forever and ever and ever, if you zoomed in, you're always going to see space between the x-axis and the graph. But if you found the area under the curve, which is our second semester thing, the area under the curve from -infinity to infinity, it equals 1. So that's kind of like a paradox, right? How can you have a finite area if you have an infinitely unbounded region, right? Wow. Okay, we'll talk about that later. It has to do with the limit, of course, but because the area underneath it is 1, you can use it as a probability density function. And just kind of as a rule of thumb, if you know what the population mean is, then roughly 68% of the observations are going to fall within 1 standard deviation of the norm, right? It's where the majority of the observations live. And if you look at 2 standard deviations away, then you're talking about 95% of the observations, and then it goes on from there. 3 standard deviations away, now you're pretty much talking about everything, 97.5, whatever. But there are always these, not outliers, but really uncommon occurrences that occur in what we call the tails, right? Either on the low end or on the high end, okay? You can figure out the probability that an observation is going to live anywhere by looking at the area under the curve up to that point, okay? But the standard deviation, that is, how do you measure that distance between those marks? It comes down to what is the distance from the local maximum to your inflection value, okay? This distance right here establishes the distance, okay? Now, how do you find the inflection values from the curve? It's hard to pinpoint them, right? We can see the local max is right there at the top at the x value, but the inflection values are more nuanced, okay? So what I want to do is take this, which is the general equation for the standard normal curve with a population mean mu and a standard deviation of sigma. But for the standard normal curve, mu is 0 and the standard deviation is 1. I just want to show you that the inflection value occurs at x equals 1, right? So if you look at it like this, we want to figure out where this is right here. And since sigma is 1, this distance should be 1 unit, okay? So That's all that word says. Now, I don't expect us to take the derivative of this. So this is another good opportunity to use the calculator. So let's go ahead and set up the equation first with the following parameters. Okay. It's going to be 1 over the square root of 2 pi when sigma is 1. And that's lowercase sigma, by the way. And then times e to the negative 1/2. And it's going to be x minus 0 divided by 1, which is x squared. So there's the specialized equation for the standard normal curve. Now, if we go to the calculator, I'll go over here, and I knew you all were coming, so I went ahead and typed it in. I have it in Y1 right there. Okay, so we can type it in. Now, if you hit zoom 6, right, zoom 6, you're not going to get much. You're going to see that little line above the x-axis. But if we hit zoom 2 in, it's blinking at the origin. We can just hit enter. We get this slightly better look. All right. Now that's not a bad look. I want to change it though. I want to change my window. Negative 2.5 to 2.5 is okay. I want to change the Y min, Y max. I want to go negative 1 to 1. I just want to stretch it out a little bit more. Okay. And you can figure out what the y-intercept is, right? Plug in a 0 for x, you get e to the 0 is 1. So that's at 1 over the square root of 2 pi. But there it is. Now the inflection point, I claim the inflection point is going to be right there where that first tick mark is, because I left my scale on at 1. And it's reasonable to see that that's where the curvature changes, but I want to prove it. So here's what we want to do. I want to know where is my second derivative equal to 0. Okay, and then I want to look for a sign change there. We're not going to take the derivative by hand. So here's what we're going to do. We're going to go back to y equals. We're going to turn y1 off. Okay, we're not going to delete it. But remember, you can go to the equal sign and hit enter, and that gets rid of it. Now in y2, go ahead in y2 and take the derivative of y1. How do we get the derivative to show up? Math 8, right? Math 8. And then we recall it from y1, alpha trace, and then we do it for all x. Now, I don't want to graph that either, because that's the first derivative. I want the derivative of that. So go ahead and turn that one off, hit enter on the equal sign, and we'll do it one more time. I think your calculator can do it twice. In y3, let's take the derivative with respect to x, math 8 again, of now what's in y2, and we'll do it for all x. I want the calculator now to sketch the second derivative for me on that interval. All right. I hit graph. Notice I went from negative 1 to 1 on purpose, just so I can keep my x-axis in the middle here and I wouldn't have to change window. Oh, I didn't turn it on. Sorry. I turned it off. I never turned it back on. How do you turn it on in Y3? You say, oh, hello there, Y3. How you doing? Looking good today. Now we turned it on. All right, so here it comes. Here it comes. Yep. So there's definitely one inflection value there, because not only will the derivative change signs, right? The second derivative, that is. And look at here, there it is, right? Now, you could graph 0 and y4, whatever, and find where they intersect. But since I'm suspecting that it crosses at 1, which is 1 standard deviation away, I can actually hit trace 1, enter. Is that confirmation that it's a 0? Negative 1.6 times e to the negative 7th. Yeah, that's your calculator's way of saying it's 0, right? Remember, we're going 2 derivatives out here with data. Your calculator, that's effectively 0. Now, if you did want to go ahead and graph 0, Pretty much. I got 0 graphed in Y4. So now second trace number 5, enter, enter, enter. And now your calculator says that the point of intersection is at 1.00003. Okay. So it is in fact at 1. So there's essentially proof. So inflection values on the standard normal curve are very, very, very important values. They define what's normal and not, right? By establishing the standard deviation. Now, I want to do one more thing over here. I want you to see that your calculator, which is a number crunching machine, it can calculate slopes of tangent lines. It can calculate x-intercepts. It can actually approximate areas under curves. It's a number crunching machine. So this will be a preview of the next semester. If I want the calculator to approximate the area under this curve from -infinity to infinity, here's what I'm going to do. From the home screen, okay, remember my function is in Y1. From my home screen, second quit, there's a way to do that. Math, not 8, but if you look at math 9, math 8 is the derivative. Math 9 is the most extreme type of INT out there. It's the effing INT, okay? And if you hit it, look what shows up on your home screen. You get what's called the integral symbol, okay? And the integral looks like an S because it is. It stands for the sum. But it's the sum of infinitely many parts. Now I can't go from -infinity to infinity. So let's just try going from -3. This is your lower bound. And you can just watch if you want. And there's your upper bound. So I'm going to, math 9. I'm just going to let the calculator compute the area from -3 to 3. Now I need to put the function in here. So that's alpha trace number 1. So that's basically a Y value. And then over here, it's going to be with respect to X. Well, dx, remember, is an X value. What do you get when you multiply on a graph a Y value times an X value? What do you get when you multiply height times width? You get area. So a Y value times an X value gives you an area of what's going to be called a Riemann rectangle. And then this S just means add them all up from left to right. Okay. And I'll explain that later on. Now you calculate, it doesn't give us 1, it gives us 0.9973. But I only went from -3 standard deviations to +3 standard deviations. Let's do it again. Second enter recalls it. Let's go from -100. You can't type in infinity, right? To 100. Oops. And now the calculator, we're going to break it somehow. We're either going to break it correctly and it'll give us 1, or it's going to give us an overflow. Hey, there it is. It's 1. Okay. Now, when we study improper integrals later on in the year, you're going to see this, that not every unbounded region has a finite area. Some unbounded regions, as you would expect, have infinitely large areas, right? But some of them that are unbounded have finite areas. And it has to do with how fast does the curve go to the x-axis. If the graph converges to the x-axis fast enough, it's enough to make the area finite. Whereas if it goes to the x-axis kind of in a lazy fashion, the area is infinite. Now, here's kind of another idea where you can have an infinite process equaling a finite number. Just kind of getting off subject here a little bit, but let's think. I wrote a poem for my son a long time ago that dealt with this, and it was also to teach him, money. But basically, and I think it was in limerick form, of course, right? Let's say you start with a penny, right? There's 1 cent. And then the next day I add a half of a penny, right? Next day I add a half of a penny. right? I'm saving for his college, right? So day one, when he's born, I put a penny down. And then instead of the checkerboard example where I'm doubling the amount that I'm adding every day, I'm only adding half of what I added the day before because, teacher's salary. So the next day I add a half of a penny. And then the next day I only add a quarter of a penny. And then the next day I add an eighth of a penny. And the next day I add a 16th of a penny, so on and so forth. The next day I add a 32nd of a penny, right? Yeah. Well, could I keep this process in theory going indefinitely?
Yes.
Yeah, I can keep adding half of what's the previous sum was, a 32nd, a 64th, so on and so forth. And I can do that forever and ever and ever. But as I keep adding more and more and more of less and less and less, it's only approaching a finite sum, right? You might think, oh, keep adding something forever and ever and ever, keep adding a positive amount forever and ever and ever and ever. Why, that's going to grow to infinity over time. But this is not, right? You could see visually that I'm only eventually going to be approaching adding that whole second penny. So at the end of infinitely many years, if I keep this saving for college thing going at the same rate, by the time he's infinitely many years old, ready to go to college, he'll have almost 2 pennies to spend, right? This is approaching 2 cents, right? So it's an infinite process. I keep adding more and more and more, but it's approaching a finite value, not infinitely large. So again, this is what we're doing. 1 plus a half plus a fourth plus an eighth plus ... This only equals 2. It converges to 2. There's a limit idea built in there. What about this? What do you think? 1 plus 1/2 plus a third plus a fourth plus a fifth. Do you think that's also going to be approaching a finite value? It's going to be at least 2 cents, right? Because I've contained, I've contained that in there, but I'm adding a little bit more, a third, a fifth, a sixth. Guess what this one approaches? That one approaches infinity. Wow. Same idea, right? I'm adding less and less, and the limit of what I'm adding each day is approaching 0, right? But this one grows infinitely large, and that one grows to 2. So anyway, my wife said to do the bottom one, but I was like, no, I did this one. I should have listened to her, right? Have more money by now. That's interesting. And again, it has to do with how fast those terms go to 0. The top one goes to 0. The terms go to 0 a little bit faster than the bottom terms go to 0. So anyway, that's a preview of second semester stuff. So anyway, we're done with 3.5. There's a lot to it, but it summarizes a lot of really, really important things. Okay, so how much time do we have left in here? 8 minutes? Okay. I'm not going to start the next section today, but here's kind of the idea. I don't think I'm going to spend any more than 2 days on optimization, okay, which is the next section. It's word problems. And then after that, we have related rates, which hopefully I'll spend no more than 2 days on that. I have some trimming off of the optimization worksheet to do. This worksheet is 14 pages, but hopefully you'll see, especially if you work it from the back forward, it'll go pretty quickly. The optimization assignment right now is a bear. It's a booger. So I'm gonna have to trim some of those off. I really like optimization, and so I always overteach it. I always go way more than College Board expects you. And maybe we'll return to that after the AP exam, and we'll look at some more non-typical optimization type questions. Okay. But I'm gonna try and be the math butcher now and trim off the fat. So we can get to chapter 4, which starts getting into integration and finding areas of irregular regions. Okay. So use the rest of the class period today to do whatever, to work on that worksheet, which is due Monday. I'm really pushing it out there, but we're starting the next section tomorrow. I don't care. As long as you go to the bathroom on your way to lunch. Yeah, okay. Does that make sense, everybody? Good? Yeah, we're good? All right, awesome, good, all right, cool, awesome, well, all right. Have a good lunch. Have a good day. Yeah. Oh, yeah, real quickly, while I still have all y'all. Landon and Devin Keeling are going to start doing AP review / teaching sessions during 7th period. So if you have 7th period off and you're still around and you want to start coming, they want to do that just to help y'all. If you are serious about passing the AP exam, I've given them access to a bunch of AP questions starting next Thursday during 7th period. They're going to be reviewing stuff that we've covered, anything up to now, from limits all the way up to now, and they're going to be throwing actual AP questions at you. Okay, so, and they'll be doing that for the rest of the year. Okay. Okay. So keep that in mind. Free up your 7th period. That's a win-win for everybody. Win-win-win.